Hi everybody, Matt Morgan here. In this section we're going to talk about acids, bases, and neutralization from Wiley section 6-6. We'll talk about strong acids and bases, acid-base neutralization reactions, and give examples of total and net ionic equations from acid-base neutralization. So you've seen this picture in Wiley. The picture's from section 6-6.1. It says muriatic acid. If you've ever maintained a swimming pool, you might have added muriatic acid. It sounds like a long fancy name, but it's just the traditional name for hydrochloric acid, HCl. Why don't they call it HCl? Great question. But I just wanted to share that bit of information. HCl is considered a strong acid, and the word strong has a specific meaning in terms of acids and bases. There are 6 strong acids and about the same number of strong bases. If you memorize these now, it's going to do you a lot of good. It will do you good now in Chem 1, and it will do you a lot more good in Chem 2 as well. Strong acids and bases have specific properties. It will be good to identify an acid as a strong or a weak acid. Now, any acids or bases not listed in this table can be considered weak. What we mean by a strong acids and bases, when dissolved in water, completely break up into their component ions. With something like HBr, which is one of the strong acids, hydrobromic acid, there is no molecular hydrobromic acid dissolved in water. It all breaks up into its H+ and Br- ions. So if you take Chem 2, there's a whole chapter on acids and bases. This is just an overview for now. It's good to know now that acids add H+ ions to solution, while bases add OH-. So what happens when H+ and OH- combine? An acid combined with a base makes water. There's our reaction. OH- and the H+, the plus and the minus, attract each other. The result is a neutral H2O molecule. So you can't just have a bottle of H+ ions or a bottle of OH-. You have to have a negative ion to counteract the H+ and a positive ion to counteract the OH-. Hydrochloric acid is a combination of H+ and Cl-. Sodium hydroxide is Na+ and OH-. So when we add these together during an acid-base neutralization, the counter ions, the chloride and the sodium, react as well. The reaction that we see is HCl plus NaOH gives us NaCl and water. Here's an illustration of the sodium hydroxide, hydrochloric acid molecules coming together, switching partners just like they talked about in the precipitation reaction. Our products then are sodium chloride and water. So we say that the products of an acid-base neutralization are water and a salt. In this particular reaction, NaCl, the salt is table salt, but any compound that isn't water that results from an acid-base neutralization is considered a salt. Here's another example of an acid-base neutralization. We have perchloric acid and lithium hydroxide going to lithium perchlorate and water. In this case, the salt is the lithium perchlorate. There's our hydrochloric acid sodium hydroxide neutralization, the perchloric acid and lithium hydroxide neutralization. So in chapter 6 so far, they've talked about ionic equation, states of matter. Notice I haven't put any states of matter in here yet, but we will. Strong acids and bases are always soluble in water. They will have a subscript AQ for aqueous. water is designated as a liquid. The salt that results from a neutralization is usually soluble, so it will be aqueous as well. The molecular equation for our acid-base neutralization, HCl aqueous, sodium hydroxide aqueous, gives us sodium chloride aqueous and water, which is a liquid. The other reaction, aqueous perchloric acid, aqueous lithium hydroxide, aqueous lithium perchlorate, and water. So just as we've done before, we can write the total ionic equation for a neutralization. We do it the same way as we do for precipitation reactions. The aqueous products and reactants are written as separate ions, separated from each other, surrounded by water. So this is our first neutralization reaction. We write this as H plus aqueous plus Cl minus aqueous plus sodium plus aqueous plus OH minus aqueous, there's our reactants, going to Na plus aqueous plus Cl minus aqueous plus water. Water is together liquid as a single molecule. To get our net ionic equation, just as before, we cancel out spectator ions. Spectators in this case, chloride, the exact same on reactants and products. Our sodium ion cancels out. This leaves us, for our net ionic equation, H plus aqueous plus OH minus aqueous going to our liquid water. Let's do one more example, our perchloric acid lithium hydroxide reaction from before. There is the molecular equation. When we write the total ionic equation, we'll write out H plus aqueous plus our perchlorate ion, aqueous, plus lithium plus aqueous, plus hydroxide. Now this takes a lot of writing. You've got to give yourself a lot of space when you write this out, but this isn't conceptually difficult. Our products are the lithium ion, perchlorate ion, and water. That is our total ionic equation for this neutralization. Like before, to find our net ionic equation, cancel out the spectators, our perchlorate, our lithium. We're left with our net ionic equation. H plus aqueous plus OH minus aqueous goes to liquid water, just as before. So if you have a neutralization reaction and one of your products is a soluble salt, the net ionic equation will be H plus OH minus going to liquid water. Good thing to remember. In this lesson, we discussed acid-base neutralization reactions. We wrote the total and net ionic equations. If you are taking Chem 2, this information will be seen again. Don't forget it. As always, contact a course mentor if you have any questions. Here is our contact information. The main job of your course mentors is to enable your success in these courses. You can email us at the group inbox at chemistry@wgu.edu, or you will find contact information for your individual course mentor in your course of study.